Good afternoon, everyone. Welcome to the 17th International Conference on Network or Service Management. My name is Sabuzima Nayak. I am a PhD scholar from National Institute of Technology, Silchar, India. Today, I am going to give a presentation on our paper titled CountBF, a general purpose high accuracy and space efficient counting Bloom filter. Bloom filter is a membership checking data structure introduced by Gordon Howard Bloom in year 1970. This figure illustrates the architecture of Bloom filter. Counting Bloom filter have another variant called counting Bloom filter. Our proposed system is based on this. This figure illustrates the architecture of counting Bloom filter. Our proposed counting Bloom filter called CountBF is implemented on 2DBF. 2DBF is is another variant of standard Bloom filter, which is a two-dimensional integer array. In counting Bloom filter, each cell has one counter, whereas our CountBF has multiple counter in each cell, and the bit length of each of the counter can be defined by user. This figure illustrates the architecture of CountBF. Here we have taken a 8-bit counter. Suppose each cell is a beta length, then 0 to 7 bit gives the first counter, then bit 8 to 15 is second counter, 16 to 23 is third counter. So similarly, we can have multiple counter in a single cell. In our algorithm, we are using two types of mask, extract mask and reset mask. Extract masks are used to extract certain counter value using bit operations. They are predefined for each bit counter. For example, suppose we consider an 8-bit counter, then these are the 8 reset masks, extract masks. Reset masks are used to reset the counter value to 0. Similarly, they are also predefined. These are the 8 reset masks for 8-bit counter. This is the CountBF performs three operations: insertion, query, and deletion. This is the algorithm for increment. This is the algorithm for insertion operation, where we want to insert item W into CountBF with the dimension x and y, and we are using k number of hash functions. So for k number of times, we will hash the item W, and the hashed value is given as a parameter to function increment. This is the algorithm for increment function. First, we obtain the cell location and the required counter number. Then the counter value is extracted using extract mask. The counter value has trailing zeros, so we remove right shift operation. So we perform right shift operation to remove them. Then we increment the counter value. The new counter value is checked. If it has reached max value, then counter overflow will occur. So the operation is terminated. Otherwise, continue. Otherwise, we will continue. Then using reset mask, the old counter value is removed from the cell and new counter value is updated using OR operation. This is the algorithm for lookup operation. For k number of times, the item W is hashed and passed as a parameter to function test. If all k test function return true, that means the item is present in CountBF, otherwise absent. This is the algorithm for test function. After obtaining the counter value, it is checked. If it is greater than equal to 1, then return true, otherwise false. This is the algorithm for delete operation. After obtaining the counter value, it is decremented. If the new counter value is less than 0, then operation is terminated, otherwise continue. Then same procedure similar to insertion operation is followed to update the new counter value. In our experiment, we have used 4 data sets: insert set, mix set, disjoint set, and random set. Insert set is used for insertion and other sets are used for query operation. Insert set consists of integers from 1 to n, where n is 10 million, 20 million, 30 million, 40 million, 50 million. Same set is equal to insert set, that means the integer that are inserted into CountBF is given as values. Mixed set has half of the integer that are present in same set and half of the integer that are absent in same set. Disjoint set has integers which are absent from same set. Random set are random integers within the range of 1 to n. These are our experimental environment. For our experiment, we have considered 6 bit length, that is 3 bit, 4 bit, 5 bit, 6 bit, 7 bit, and 8 bits. And we have also compared our CountBF in another 2 types of Bloom filter, that is standard Bloom filter and counting SBF, that is standard Bloom filter, and CBF, which is counting Bloom filter. This figure illustrates the insertion time. The x-axis represent the data set, means the number of item inserted, that is 10, 20, 30, 40, and 50 million. Then y-axis represents time in second. In all cases, CountBF took the highest time, which is 5.2 second in 10 million and 26.91 second in 50 million. In 10 million, lowest time is taken by 4 bit. In 20 and 30 million, lowest time is taken by 8 bit. And in 40 and 50 million, lowest time is taken by 7 bit. So overall, in insertion operation, 7 and 8 bit CountBF exhibited best performance. We have performed the query operation for 10, 20, 30, 40, and 50 million, but due to time constraint, I'm going to discuss only the 50 million. Uh, this figure illustrates the 50 million lookup time by CountBF. We are x-axis represents the data set, that is same set, mixed, disjoint, and random set. Y represents the time in second. For query operation, for all data set, CountBF took the highest time. In same set, CountBF took highest time of 24.53 second and lowest time in random set of 14.877 second. In 50 million, 6-bit CountBF exhibited better performance. And overall in query operation, 7 and 8-bit CountBF took the lowest query time. In same case, I'm only going to discuss about 50 million items. The CountBF exhibited maintained around 10 to the power minus 5 in all cases. CountBF and standard bloom filter maintain the desired false positive, that is dot 0.001. And disjoint set has more false positive probability compared to mixed and random set. The memory usage. This figure illustrates the comparison of memory consumption of CountBF, standard bloom filter, counting bloom filter. Here CountBF represent 3, 4, 5, 6, 7, and 8-bit CountBF because they have same array size. In case of 10 million, CountBF is consuming a 8.79 MB and standard bloom filter 17.13 MB and counting bloom filter is taking 68.55 MB. In case of 50 million, CountBF is taking 43.12 MB, standard bloom filter is taking 85.6 MB, and counting bloom filter is taking 342 MB. We observe that the array size of standard bloom filter is double the size of CountBF, and in case of counting bloom filter, it is 8.5 times compared to counting bloom filter. Conclusion. We have proposed a novel counting bloom filter variant called CountBF, which has multiple counter in a cell. CountBF can insert, query, delete an item in peak of k time complexity while preserving high accuracy, low false positive probability, low memory footprint, and fast execution time. CountBF significantly improved over standard bloom filter counting bloom filter. It has has lower false positive probability and higher accuracy. These are some references of my paper.